Okay. One other thing that we can do is what's called an orbital diagram. And this gives us a bit more detailed information on how the electrons are arranged within the atom and within the specific orbitals. Now, when we do electron configuration, typically we use circles or squares to represent the orbitals, and we'll use arrows to represent the electrons. Now, let's place our orbitals. 1s, that's one orbital. 2s, that's one orbital. 2p gets 3 orbitals, like so. It's like playing solitaire, right? 3s gets 1, and 3p has 3 orbitals. Regardless of the number of electrons that are present, each sublevel will always get the same number of orbitals. S is 1, P is 3, D is 5, and F is 7. Okay, so next we'll distribute the electrons into the orbitals. And again, silicon has 14 electrons. So 1s gets 2 electrons, like so. And 2s, we have 2 electrons. Up and down arrows, because the electrons have opposite spin within the orbitals. Spin being a word that refers to their motion within the orbital. And again, electrons are negative, so they'll repel each other. So their motion is opposite of each other within the orbital. 2p6, we're going to fill these up, and we'll follow Hund's rule here. So we'll fill them in individually first, and then we'll go back and we'll double up here. 1, 2, and 3. And the result is, yes, each orbital here in 2p has 2 electrons in it. Finally, or not finally, but next we have 3s with 2 electrons. And finally we come to the highest energy orbitals, the 3p, with 2 electrons. So those are going to be filled in like this, 1, 2. And again, Hund's rule, we're filling the electrons in individually. We're not doubling them up because there is space to do that. Now, the usefulness of an orbital diagram is that this can help explain why silicon would react the way it does with other elements. In the 3p orbitals, silicon still has space for 4 electrons. So when it forms compounds, accept 4 electrons into these empty p orbitals, or it will lose 4 electrons from its highest energy orbitals to make 2p the highest energy level of valence electrons. Silicon is a metalloid, and so it will go either way depending on what it reacts with. But again, the orbital diagram can help us understand how an element will react with other elements in the periodic table. And again, this is a way of representing where the electrons are within the orbitals of the various sublevels and energy levels. Orbital diagrams.